Stanford University.
I'm Keith Devlin. Welcome to this continuing studies course. In fact, in many ways it's not a course. It's a tour of different parts of mathematics. So it's a series of somewhat disjoint lectures. There is a theme to it, insofar as there's a theme to the book that I've suggested. If you want a book, it's sort of loosely based on my book from, I think, 15 years ago now, Mathematics, a Science of Patterns. No, not that one. It's The Language of Mathematics Making the Invisible Visible. That's the one that I suggested. There's two or three I could have suggested. That was the one that I'm sort of loosely suggesting we do it as the textbook, or at least as a reading book. One or two things in that book are a little bit out of date. Other things I would do with them differently if I was rewriting the book, and sometime or other I will rewrite it. But you know, mathematics, even though some things have changed, by and large the central core of mathematics moves at fairly glacial pace and doesn't change an awful lot in decades. It changes quite a lot in centuries, but decade by decade it doesn't change too much. So it's a series of somewhat coherently connected, but in many ways disjoint talks about mathematics. And as we go through, I'm going to try and make sure that by the end of the 5 weeks, we've sort of covered the basic ideas of mathematics, some of its history, some of its cultural and social aspects, some of its internal mechanics, some of the things that turns people like me on. Actually, I've had two careers. I had a long career within pure mathematics when I was just interested in doing mathematics. And then since the 1980s, the work that actually brought me to Stanford in the middle of the 80s was very much applied work. Applying mathematical ideas in areas of communication, reasoning, communication, and things of that nature. And then more recently, I've got interested in use of technology in education, which is partly why I got involved in giving one of these online courses, and also creating an educational video game company to develop educational video games for middle school mathematics learning. Okay. This is the name of the course, Mathematics Making the Invisible Visible. We've got 5 weeks, the 5 Mondays which fall under in October of this year, 7 till 9, till 8:50 each night. My goal is that we'll break it into 2 parts. There'll be one part, then we'll have a break of 5-10 minutes, and I've now discovered that the bathrooms are just along left out of that door and down on the left. Take a little break, and then we'll finish the second session, second half of the session. And then starting next week, I'll try to make it a little bit more interactive, and that's when the roving camera will go around, and we'll sort of have people trying to do some things. Okay, we're not going to put people on the spot, and I'm not going to ask you mathematics questions in that sense, but it will get you to sort of do things. Okay, so first lecture, general overview and the development of numbers. So we're going to start at 35,000 feet, take a general look, both historical and contemporary, and then when we've done that, I'm going to start zooming in on particular areas of mathematics, and I'm going to begin with numbers, which is essentially where mathematics as recognizable stuff began. Okay, so first question is, what is mathematics? I always begin with that because, for sure, or almost for sure, if you come out of the high school, you haven't a clue what mathematics is, which is why when students come out of the high school and get to university to major in mathematics, they have one really disturbing first semester or first term, because they discover it's not at all what they liked. And it's sometime during that period when many high school math whizzes drop out and do computer science or engineering or something else, and the occasional arts major or classicist major intended suddenly gets turned on to mathematics when they discover it's a creative discipline that allows their creativity to be applied in different ways and is challenging intellectually, and then they get turned on to mathematics. And there are many cases of famous mathematicians, some of them here at Stanford, who began doing other things. In one case, someone was a juggler, and a magician, and then ended up with an endowed chair here at Stanford. Okay, so the basic questions are, what is mathematics and what does it do? The answer to that question, or the answer to both questions actually, particularly the first one, they've changed over the years. You go back, certainly go back to 1000 BCE, then there really wasn't mathematics. People were doing things in the world, they were measuring things and counting things, but you really only get something that's recognizable as mathematics around 500 BCE, somewhere around there. And that was really when people began to study it. The ancient Greeks were one of the civilizations, not the only one. You can trace it back to China and Japan and South America. But the Western tradition that we inherited can be traced back fairly clearly to the Greek mathematicians. Parts of it before then, but as a discipline, you could certainly, it's a reasonable case to say you can declare mathematics as something recognizable in modern terms, as beginning with the ancient Greeks. And this was the era of Euclid and Aristotle and so forth. And in the course of that, they changed it from the study of number, which can be traced into, Babylonians had some study of number, various other civilizations had study of number, the Egyptians. But with the ancient Greeks, you've got a very definite, recognizable form of mathematics. And it wasn't just number, it was number and shape. They were very, and the integration between the two. So essentially arithmetic and geometry and the beginnings of what we might call algebra. And then it sort of grows and develops, but broadly can be regarded, this is the 35,000 feet view. Things look different when you zoom in. But broadly speaking, as you go through that period, it's the same discipline, just gets richer and broader until the 17th century when we get calculus being invented simultaneously in England and Germany by Isaac Newton and Gottfried Leibniz. And that enabled the tools of mathematics to be extended to study continuous motion and change, and in particular shape, space, the activities in space. A lot of that driven by astronomical considerations. And then it sort of develops from there. You get other disciplines coming along, but still recognizable as a whole. The next, I would say, from 35,000 feet, the next major change is what occurs in the 19th century when attempts to understand what makes calculus work, which lasted well over 200 years, those attempts, led to really a sea change in mathematics because it had to turn in on itself, examine its own tools, its own concepts, its own presuppositions. And we get, in particular, we get the subject known as modern real analysis and modern complex analysis developing. And that was driven in large part by trying to understand what makes calculus work and why it was so darned effective. And in the process, the nature of mathematics very much changes at the end of the 19th century. Prior to that, it was essentially about calculation and computation. It was very algorithmic. You perform some computation, some calculation to get an answer. It was very much about getting an answer. End of the 19th century, late 19th century, particularly starting in Göttingen in Germany and emanating from there was really a revolution in that mathematics changed from being about computation and calculation to get answers to understanding relationships and to think in terms of concepts. It was all about concepts, relations, and understanding. And the reason was that the mathematicians of the 19th century realized that the tools were very powerful, but they didn't fully understand them, and they had to turn to understanding and relationships. And that's really changed the nature of mathematics. And this is really why students that get to university have difficulty, because the school system is still rooted, actually most of it's rooted in the 13th century, but some of it takes you up to the 17th century. And it certainly doesn't take account of what happened in the 19th century. And universities are all about mathematics. That's essentially, by definition, is post-19th century, even the stuff that builds on the older stuff. So the whole concept of mathematics changes. Okay, and that gave Tom Lehrer one of his best ever songs, but that's the way it goes. So the nature of mathematics has changed. And if you want to answer what it is today, there's really no simple answer that's satisfying. The answer, I was one of the people who back in the 70s or thereabouts, I wasn't the first person that came up with this, but I was one of the people that pushed hard for this meme to be accepted as capturing mathematics. Not because it really captures mathematics, because it begs the question of what kind of patterns are you studying and what are the tools with which you're studying them. But it does at least distinguish it from calculation and computation. So we very consciously, a group of us in the 70s and 80s, mainly in the early 80s, I guess we pushed this. I wrote a book with the title The Science of Patterns in sometime in the 90s. I think 1994 that was. We very much pushed the adoption of this, and it's actually taken hold. I sometimes wish we hadn't, because it gets misunderstood. But at least it was meant to sort of put a stake in the ground as to what modern mathematics was. Another way you could describe it would be the study of abstract structure, which again begs questions as to what kind of abstract structure and how do you study them. But subject to that elucidation, that further elaboration of what these mean, that captures it. Okay? That really does sort of say what modern mathematics is about. So the mathematician, in terms of dealing with the world, I mean, different disciplines look at the world in different ways. You know, the painter looks at the world in one way, the poet looks at it a different way, the novelist looks at it a different way. People with different training, different perspectives, look at the world in different ways. You know, Picasso looked at the world and saw things, you know, that in a way we didn't. You know, he draws a bull, and we can recognize it as a bull, but it sure doesn't look like any bull you see in a field. So you look at these drawings that people do, and they can capture essences in the world. And in fact, I think artists like Picasso and Miro are very, very much like mathematicians. In what they did was they looked at the world and they abstracted to the very bare essentials that resonate with the human mind. In their case, they resonated in a sort of a deep human emotional level. With mathematics, there's a logical element as well, but the mathematician extracts from the world patterns that resonate in a sort of logical way with our cognitive system. Now, and there's some interesting features of that I'll keep coming back to. One of which is that when you do that, you have this incredibly powerful feeling that you're making discoveries of things that are already there. And it's certainly the case that mathematicians all over the world, when they come in and develop a new concept, in many cases they arrive at the same concept at the same time, the same results at the same time, and they have no difficulty understanding each other, with one or two difficulties at times, but by and large they have no difficulties understanding each other. And so there's this real sense that mathematics is common. Well, there's a sense that it's actually out there to be built, to be discovered rather than to be built. It's a very powerful feeling, and I've certainly had it all my career. I'm not sure you can really defend it. I mean, the only thing I could defensively say is that whatever it's capturing, well, certainly it's capturing how human beings encounter the environment. But the human being's part of that. And so it could be that the patterns of mathematics are really reflecting not the universe, but how the human cognitive system interacts with the universe. Well, we'll almost certainly we can keep coming back to that thing. And then you get into discussions of is mathematics discovered or invented. I think actually neither of those terms really reflect what's going on. But to think of it as a sort of an objective study, I think is indefensible, although it's powerful. Okay. To flesh out that definition, you really need to say what kinds of pattern you're talking about, to give some examples. And the list gets very long. Initially, we have patterns that arise in counting, numbers. When you bring collections together and you put a number, if you like, on the size of the collection. Actually, people counted before we had numbers. Counting began at least 35,000 years ago, and that involved piles of pebbles, notches on bones that have been discovered, probably notches on sticks, but they tended not to survive. So we've got artifacts that go back 10, 20, 30,000 years or more that suggest people were counting, but numbers are much more recent. We'll get to that later on this evening. But you don't need numbers to count. Numbers are things that that you need for arithmetic, essentially, if you want to do abstract studies, abstract reasoning. But the idea of counting is very basic. Civilizations tend to come with that all over the world, and that gives rise to numbers, and then when you have patterns of numbers, you get arithmetic. The numbers themselves have patterns, things like even and odd, primality, all sorts of other things you can talk about. That gives rise to this rich and powerful discipline known as number theory. So this is mathematics turning in on itself, and the ancient Greeks did this, turned it in. So did the Babylonians to some extent. They turned it in on itself and looked at the patterns exhibited by the objects that had arisen as pattern abstractors from the real world. You have patterns of shape, giving rise to the subject geometry, coming from the Greek measurement of the earth. Then you actually have measuring, and you can measure in conjunction with space, with shape, and you get trigonometry. Patterns of motion and change is calculus, which we usually identify as beginning in the 17th century, although many of the ideas had been discovered by Archimedes, thousands of years ago, 1,000 years, more than 1,000 years earlier. Patterns of putting things together and looking at the relationships between them and different ways you can put things together, that gives rise to algebra. That's one conception of algebra. That's modern algebra. We'll talk about another version of algebra next Monday. Patterns of symmetry, a branch of mathematics known as group theory. And then a bunch more. Position and closeness is a relatively modern discipline, 20th century discipline essentially. Well, began in the 19th century, but developed strongly in the 20th. Position and closeness, that's topology. Patterns of reasoning, that goes back certainly to the ancient Greeks, the branch of mathematics known as logic. More modern patterns, we've got dynamical systems, which gives rise to dynamical systems theory. Somewhat unimaginative title for the theory, but there we are. 17th century, we've got patterns discovered in the repetitions of chance events. We've got probability theory coming along. And patterns of real-world data, we've got statistical theory, the mathematical part of statistics. So we've got, and there are many, many more. You could keep on enumerating these. These are some of the highlights, some of the more famous ones. So that's a quick survey. So I think it's only really by listing these examples that you get a sense of what kinds of patterns are studied. So that's an illustration of some of the patterns that are studied in mathematics. And then the question is, what is it good for? I mean, that's the question that those of us who teach mathematics for a career, we dread the moment at the end of the class where the student says, what's it good for? Well, one reason it's good and useful can be traced back to Galileo, who essentially founded modern science by realizing that if you apply mathematical perspective, numerical quantitative perspective to the world you live in, you can make an awful lot of useful conclusions. And this is a paraphrase. I mean, he wrote it in Latin anyway, but this is a loose paraphrase of what he wrote. To understand the universe, you have to understand the language in which it's written, and that language is mathematics. And that gives rise to physics, is essentially the world looked at through mathematical eyes. Now, whether that denigrates or elevates physics is really up to you. I say that in admiration of physics, actually. But that's Galileo's approach to the world, and it was very, very powerful. Instead of trying to understand why things happen, understand the degree to which they happen and the degree to which they're related, and look for quantitative relationships between things. Forces, mass times acceleration, and all of that stuff that comes out. And when you think of it, force, mass, and acceleration are pure abstractions of mathematics. Temperature is a pure abstraction. It's all of these things, force, mass, acceleration, temperature, pressure, they're simply figments of our imagination that allow us to hang numbers onto the world. A la Galileo, and when we hang these numbers onto the world, we can say, oh yes, force is related to mass times elevation, and we can do all of that stuff. And I'll give a specific example in a minute. And here it is, in fact. That's a very fast minute. Here we've got a very famous equation called Bernoullis Equation. And what's it good for? Well, it's good for several things. One of the things you can do with it is you can use it to help understand what keeps an airplane in the sky. But I should stress the word helps, because I'm going to come back to this in a minute. Because one of the things I want to do during the course of the next 5 weeks is dispel a lot of myths that are floating around on the internet. It was bad enough before we had the internet. Myths would spread. Now myths can spread at almost the speed of light, and they do. And so I'm going to try to knock some of them on the head as we go through. One of which is that Bernoullis equation is what keeps an airplane in the sky. No, it's not, but we'll come to that in a minute. How does one of these devices from Cupertino, or designed in Cupertino, how do these devices store music? Well, they use this kind of stuff. mathematics that was developed originally in the 19th century to understand heat flow. What comes around, and so this was 19th century mathematics brought up to date and sort of discretized, and it gives us a way of encoding music and sounds as sequences of numbers, if you like. Here's a nice quote from Graciela Cichelnitsky, the economist of Columbia University. She got a PhD at Cal Berkeley. All of the very dynamic sunrise sectors of the world economies are merging between themselves and altering themselves through the use of mathematical tools. This is really nice. Mathematics works for today's society like the fossil fuels worked for the industrial society. Today, to get energy, we don't burn fossil fuels. Now, to get knowledge, we use mathematics.
The world economy is about to take a somersault. In the sense that we are changing the way we produce goods, the ways they're circulated, the way we work, the way we think about things. But we are now seeing a new wave of change.
There have been three great eras in human history. And in each era, humans relied on different resources for survival. In the first era, humans were hunters and gatherers. They relied on physical strength and their ability to find food. In the second era, humans became farmers and they relied on controlling the land. In the third era, the industrial age, humans relied on the power of fossil fuels and machinery to drive the economy. Today, Cichelnitsky and others believe that we're heading into a new age.
Now the industrial society is becoming a different type of society. And this different society I call the knowledge society. And this transition that we're going through, I call it the knowledge revolution.
As part of the knowledge revolution, we will all rely on a new powerful resource.
Mathematics is the raw material, is the energy that drives the system. Mathematics is like the fossil fuels were for the industrial society. Now, to get energy, we don't burn fossil fuels. Now, to get knowledge, we burn mathematics. We use mathematics.
Anyone who lives in the middle of Palo Alto is surrounded by this all the time. So that's an example, I would say, of using mathematics to understand the world, outside-in use of mathematics. You look at the world and you apply mathematics to understand things. And in today's world, we do an awful lot of understanding networks and infrastructure and things that connect people together. Another example is improving athletic performances. And here's another nice quote. Great coaching and good intentions are not worth anything unless the goal is correct. The mathematical analysis is like turning on a light in a dark room. This is reflecting the fact that at the highest levels of athletics, the people who go for gold medals in the Olympics, you're at a level of performance where everyone's within a fraction of a percentile of equality. Everyone is really close in ability. They're fully trained, they have good diets, they have the right equipment. And the only edge you can get, you may be looking for half a percentage of performance. And mathematics can very often yield 1 or 2% if you apply it well. And one of the more famous studies was when there was the study to figure out how to do the triple axel a few years ago. And I got a nice little quote from Kathy Casey.
We did find out that you're not in the air any longer, which is amazing. That's very, very interesting. You're not in the air any longer.
Before the study, we believe that you need to throw your leg out further for a triple. In reality, it needs to be closer, so you can get into the air and into your rotation much quicker.
That was better. Let's go over that. All right, ready? Step up, quick, up, quick. Good. did better triples because it was who could pull in quick and tight with their arms that made that extra rotation.
It wasn't terribly new mathematics. It was some trigonometry, some calculus, some Newtonian mechanics, coupled with high-speed film and measuring angles and doing simulations on computers. But it was just a very good modern use of some fairly old mathematics. Again, that's what I would call outside-in use of mathematics, using mathematics as a sort of spectacle lens through which to filter the signals coming from the world and make sense of them in a useful way. Not the artistic way, but in a scientific way that allows you to do things. So again, different ways of looking at the world. You can also use mathematics in reverse. You can use it to take ideas in your mind and put them out, which is what happens at Pixar and places like that. And one of my favorite examples, mainly because I'm of the era, not just Jackson Browne, but 2001 and Blade Runner. So, you know, Doug Trumbull is one of my heroes of my youth. And here's a nice quote that he gave a few years ago. "Mathematics is a sort of hidden tool for me. In the world of computer graphics, mathematics is behind everything I do."
We're given the human physiological senses, our ears, our eyes, our bodies, much more information, and that draws us into the movie like a real experience. I have sort of a basic intuitive understanding of mathematics and geometry. Mathematics and numbers are behind everything I do.
So there's a sort of two-way pipe. We can use it to understand the world, and we can use it to take our ideas and express them in the world and to build things. Okay, so just bring three guests in quickly to sort of emphasize the point I'm making about mathematics being a way of understanding the world and doing things in the world. And it's everywhere. I mean, we just look at the world around us. I mean, it always was everywhere in the sense that we were using mathematics to understand the world. But when we started feeding back into the world with the products of those mathematics, we built artifacts and we built systems all around us. You know, we've got a piece of mathematics on the surface of Mars wandering around right now. And we've got mathematics sort of everywhere. We have it in our pockets. We have it on our... I've just remembered I didn't switch off my iPhone. So my apologies if it rings. But it's all around us. Okay. Those clips, by the way, were from a TV series I made a few years ago for PBS called Life by the Numbers. A couple of interesting things about it is, the most interesting thing is this came out, I think, maybe 10 years ago now, maybe a little bit longer. A bit longer than that. Maybe 12, 15 years ago. It was certainly before 2000, so it's probably about 15 years ago this came out. So maybe it's about 15 years old this thing came out. It was 6 one-hour shows. And we surveyed the use of mathematics in all walks of life. At least half of the segments from that show are completely irrelevant now because the technologies have changed and things have changed. It was pre-Google, just. It came out and then the next year I think Google was founded. So we had a little piece on search, which looks kind of laughable looking back. So mathematics in many ways has changed very rapidly in the areas of technology and application in technology. More traditional kinds of mathematics and traditional applications have not changed so quickly. But if you're interested in that, you can get since it's all moved on, you can get the DVD fairly cheaply now from Monterey Media. I think it's probably extremely cheap now. You can probably get a free download from BitTorrent actually, but you know, as a digital author, I don't recommend people doing that. Okay. I've certainly stopped making money from this long ago, so it's past my head. Okay, let me take a little detour now. Remember that picture of the airplane and Bernoullis Equation? Okay. There's a guy called Bernoulli, very famous mathematician. And one of the things he did was not long after Newton and Leibniz invented the calculus, he was another of the inventors. I mean, he took it to another level. And he showed that you could apply those methods, not just to looking at the motion of the stars and the planets and things, but you could apply it to motions of fluids like liquids, gases and air and so forth. And this equation, if you unravel it, and if you're into equations, it doesn't take much unraveling, and it tells you how the pressure varies with airflow speed. And it says if you have fluid flowing over a surface, then the faster the air moves, the lower the pressure gets. Okay, so you push air, and we all experience something like this when we're in the shower in a hotel and there's got one of these plastic curtains. And you get in and you pull the plastic curtain, just like you're supposed to, and you put the shower on, and the curtain comes in and wraps itself around you. Well, that's not because your body's become suddenly attracted. It's because of that pressure coming in, and it sucks the thing in. And it's a similar sort of phenomenon. And the faster you put the shower on, the more it gets sucked in. Another thing you can do is you can get a piece of paper and hold it just under your chin and blow, and the piece of paper will rise. Okay. We might do that next week. It'll be a good thing to capture on the thing. You will all sort of actually blow in it, so it's fun. We'll come back to that. Okay. For example, you can use Bernoullis equation to understand backspin. How is it that the ball rises after it's left the golf club or whatever? And so if you imagine a ball going from left to right, that means that the airflow relative to the ball is from right to left. So we might as well just imagine the ball in one place and the air rolling, moving past the ball. And so you've got backspin. So the ball's spinning in that direction. The plus means that the air is getting dragged in with frictional forces on the surface of the ball. It drags the air with it and speeds the air up in that direction. And here, the direction is counter to the airflow, so it's subtractive. So the airflow relative to the ball is less there. So you're going to have lower pressure on the top. And if you've got lower pressure on the top than the bottom, it's going to rise. And that's fine. That explanation is okay. And you can use that to sort of design, putting dimples on the golf ball increases the effect. And there are turbulence effects as well. There's more to it than that. But this is part of the picture. It's not the whole picture, but it's a good part. Okay, so that's fine. That's a reasonably good application of Bernoullis law. That the ball rises during flight, you get lift. Okay, but if you go on the web, and I might add, if you read some of the manuals that were used to train that pilot who's flying you across the Atlantic, it's wrong. Now, fortunately, the fact that the pilot doesn't understand how the aircraft stays in the air doesn't matter. He doesn't need to, right? He just needs to control the thing. The fact that he doesn't understand the physics is actually irrelevant, which is good, because in many of these manuals, the thing is wrong. Okay, and here's the explanation you'll get. And this was just taken from the web. It's a standard explanation. I believed it for many years until someone sort of actually, the guy who pointed out the error of my ways was a guy called Jeff Raskin, who was the guy that really did invent the Macintosh back in the early days. And he was a keen amateur sort of flying sort of person. He built lots of model aircraft. And he pointed something out to me that made me think, oh, yeah, of course it doesn't work. Here's the explanation you get. Here's a wing, nice aerofoil shape, and the air's coming along, and the air gets forced above or below it. Okay? It's got further to travel at the top than along the bottom. And certainly wings are shaped this way. So it's got further to travel, so it has to travel faster. It travels faster, so you've got lower pressure by Bernoulli, and it lifts up in the air. Okay, that's the standard explanation you'll find all over, including the basic physics that they teach in many cases at flying school. Okay, so it says airflow is slow underneath the wing, therefore the air pressure is greater than higher. How many people have read that and found it was convincing? I mean, I did for many years, yeah. Okay. Okay, so if you believe that, you better explain that. Aircraft can fly upside down. Even the 747 can fly upside down. They don't do it very often, but aircraft can fly upside down. Why doesn't that thing just start to descend rapidly? Well, at that point, you ask yourself, and this is what Jeff Raskin said. He says, look, I'll take you out in the backyard and we'll take a modern plane and we'll see it flying upside down. So forget that one. Okay. Here's the flaw in the argument. Imagine two molecules coming along, two molecules of air, one above the other one, and they reach the wing. One goes up, then the other goes down. Why do they want to meet at the other end? Why does the one at the top speed up and say, oh, if I don't speed up, I won't meet my friend? Come on, these are molecules of air. It's just going to get there later. There's no reason to speed up. People like to speed up if they want to stay together, but molecules of air don't want to speed up and come back to the end. There's not some quantum entanglement or something going on here. There's no reason at all why that should happen. And in fact, it doesn't happen. Okay, so this is completely spurious and bogus, right? That's not what's going on at all. Convincing argument. As I say, it was a long time until Jeff pointed out, I thought, oh God, yeah, there's no reason why those molecules should come together. Doesn't hang together. Now, there's a story you can tell sort of like this, and you can certainly tell a Bernoulli story. It's not that Bernoulli doesn't apply, it's just that the standard story that you'll find all over doesn't work. Here's what really goes on. It's Newton's second law. Every action has an equal and opposite reaction. You design the plane, in fact, it's not just the wings, it's the whole darn plane, and you tilt the plane up slightly so that the air is forced downwards. There's a net flow downwards, and if the air is forced downwards, there's an equal and opposite reaction. It's just Newton, Isaac Newton, and the plane has lift. So the main force is just designing it so that the air goes downwards. And there's actually when you see a plane in level flight, it actually has a very slight angle. And here's also taken from the web, but from a much better website. I think this is taken from NASA's website, and they should know. Is there anyone here from NASA? No one here from NASA tonight. Okay. That's a pity, actually. Okay. All right. I'm pretty sure this was NASA has a really good website on what does keep things in the air. And it's all to do with this angle of attack and so forth. So the reason the plane can fly upside down is that plane that was upside down, it was still angled upwards. And so air was being pointed downwards. So it wasn't something fancy out of the 18th, 19th century to do with Bernoullis equation. It was good old Isaac Newton in the 17th century, equal and opposite reactions. What happened to that? Hit the wrong button. Okay. Well, I don't want to leave you having sold you another bill of another piece of junk. All of these two-dimensional pictures are just misleading because lift is a three-dimensional phenomenon. If you just look at the two-dimensional slice, you can tell nice stories, but they don't really work. It's really pretty darn complicated. And you've got to look at three-dimensional phenomena. So it's a three-dimensional phenomenon, but you do need mathematics to understand it. It's just that simple mathematics doesn't work. Okay, that's the end of the detour. And how are we doing on time? Oh, pretty darn well, actually. I'm speaking too quickly. Am I speaking too quickly for anybody? I mean, I'm European, and we Europeans get faster and faster and faster. So, just sort of yell out and say, "Slow down." Any questions so far? I mean. Today's meant to, as I said, today's just going to be, those of you who got in at the beginning, today's just general introduction. As we get on, I want to sort of get more interactive, get you doing things. Be a good idea next week if you all at least do bring, paper and pencil and a pad. At the very least, we'll tear off some paper and we'll all start blowing into it and doing things. So, we'll create our own example of lift. So paper and pencil will be good. Something else that will be good. If you could bring a tape measure. Just an ordinary sort of tape measure that you use for sort of measuring your waist or whatever. That would be a good thing to have. Whether we do that next week or the week after, I don't know. But things that would be good to bring were paper, a pad of paper, pencil or pen, tape measure. Even better, if you can find one, is to bring a pine cone. If you can find a pine cone, bring a pine cone. Okay, we'll do some interesting things there, and I'll destroy another bunch of myths while we're at it. So tape measure, pine cone, paper and pencil, paper in a pad that we can use either to write on or to tear out. Okay, I'll send you all an email to remind you, if I remember. If one of you remembers and I haven't sent you an email, send me a reminding email and I'll send you a reminder. Okay, giving one of these online MOOCs, you've got 60,000 people out there around the world. Within seconds of you posting anything on the website, there's a response comes back. It's unbelievably fast. You make an error, it's out there instantly. It's a very different world. Literally, it's a 24/7 environment. People working around the clock. Okay, that was the general introduction and a little aside. Now let's look at the beginnings of what led to modern mathematics and arithmetic. With numbers, addition, multiplication, subtraction. And I guess some kind of division came in. Originally, though, just addition and subtraction. the best evidence we have about how arithmetic, remember I mentioned that counting goes back thousands of years, maybe 35,000 BCE, maybe longer, using piles of pebbles probably, certainly notches on bones, probably notches on sticks. And the notched bones have been found. You have to interpret what they were used for. You know, all sorts of theories out there, seasons and phases of the moon and things like that. My guess is the one that doesn't get mentioned is probably the one that was more significant, which is probably it was an early monetary system. And I say that because the first real evidence we have for abstract numbers was money. Why do we have numbers? It was money, folks. You want to find out where numbers came from? Follow the money. Go back to Sumeria and the Fertile Crescent region, what's now mainly Iraq. And this was about 5,000 BCE. It was a period that began then, but by 5,000 BCE is when we definitely have artifacts that we are pretty darn sure, we being the anthropologists, not me, but the anthropologists are pretty sure that what happened then was the invention of numbers, and it was for monetary purposes. In other words, you need numbers to have money, because money comes in numerical quantities, one of these, one of those, 10 of these. The interesting thing is that you didn't have numbers until you needed money. So the driving force was mediating human transactions of goods. And the essential reason why numbers came on was banking. Okay? It was essentially the invention of banking. It was the first bankers. Bankers were the people essentially who applied money as mediating quantities in trade. Interesting how that's changed now. I mean, bankers now apply banking to figments of the imagination, but back then it was to back then it was to actual physical goods. Well, not quite. The rot set in immediately, because immediately you introduce money, you've got something fictitious whose value depends purely on human agreement. Okay, here was the evidence, and it was discovered in Iraq by Denise Schmant-Besserat, who I think is now Professor Emeritus at the University of Texas at Austin. She was here on the Sloan Center on the Hill for a year, many years ago. But there she was, a young anthropologist going out into the Fertile Crescent region. And all over the place, she kept finding these burial sites and these ruins of homes and things in which there were piles of clay tokens, sometimes grouped together in ways that suggested some kind of an order. And they were different shapes. Some of them look recognizable. That looks like it might be an oil jar. That looks like it could be a goose. Some of them, one of them somewhere looks as though it could be a mill for grinding corn or something. So some of them that looks as though it might be some kind of a peppercorn. So these look as though they might have been tokens for things that people would trade. Jars of oil, bales of hay, geese, oxen, loaves of bread and so forth. So the suspicion was that these were probably tokens to represent your goods. You know, if you had 5 geese to sell, you maybe had 5 of these tokens to represent them. So the supposition was, and this is a reasonable supposition because the Sumerian society was pretty complex. It was getting to be like a modern society. There was structure in the society. You know, this was this was one of the centers of modern civilization coming along. And so the supposition she made was that these were tokens that represented goods. Okay? And here are some of them. And so if you wanted to trade things, you wouldn't necessarily have to, well, you would have so many sheep and things, but maybe the sheep were in a field, but you had tokens that represented the sheep. So you would so when you trade, you would swap your tokens for somebody else's oxen tokens, and then the goods would eventually trade. And so the tokens you had in your hand represented the things you owned. That was your bank account, and it was a collection of tokens, not unlike a pocket full of change. Right? Those were the tokens, except there were different tokens for the different objects with different shapes. Okay, so the next thing you need is a way of keeping your tokens secure, because that was a measure of your worth. And so bankers came along to look after your tokens for you. And what they would do is you'd go along with it. And now I'm telling you the story that the anthropologists came up with to explain what was going on. You had your tokens, the bank kept your tokens. They would take a sheet of wet clay put your tokens in the clay, fold it up and seal it, bake it in the sun, and there was your secure bank account. All nicely secure, locked away. Okay, now the problem was, of course, if you wanted to trade, you had to break open the thing, take out the things, change them, and reseal it. Good business to be in banking. Constant need for bankers to break open the shells and reseal them and put their stamp on them. Okay, so already the bankers were there hanging on and taking our money in the process. They're 10% or whatever they were taking. So then some entrepreneurial person came along and said, you know, it's fine if we crack open the thing when we're actually doing a trade. But if I'm just making a bid on something, I don't want to pay the banker to sort of break this apart and put it together. If I want to just show my worth, why don't I, before you seal up this thing, take the tokens, impress them on the outside, then put them in and seal it. So on the outside of the sealed envelope, the clay envelope, you've got tokens, indentations of the tokens. So you don't have to break it open to see how many tokens there are. You just need to look at the indentations. That's an advance. Okay. Your worth, so you've interesting areas of abstraction now. We've now got real sheep and real geese and real jars of oil represented by artifacts, tokens. Tokens are then put into an envelope, and the tokens are now represented by marks on the outside. We're about to invent writing. Writing for those people who like to think that mathematics is supreme, as far as we know, writing numbers came before writing words. It all began with numbers, and it was all about money. So they put these tokens on, so you've got abstract markers, symbols representing the tokens and the tokens representing the objects. So you're already 2 steps removed from the real world, and you've got these tokens. And that was fine for a while. And then after another 1,000 years goes by, and then another entrepreneurial person comes along and says, you know, we don't really need those tokens inside. All you need is 1 token for each kind of object, because you can use the same jar of oil token 3 times if you've got 3 jars of oil. So you just need different tokens to make the indentations, and it doesn't matter where the tokens are. It's really all about the indentations. The tokens don't matter. They're just like the gold in Fort Knox. You know, you and I don't swap the gold in Fort Knox. It's just there. Right? You just go with the tokens. So when you do that, you can think, well, in that case, I don't really need a clay envelope. I can just have a tablet with marks on it. And here is one of the tablets. So these came later, flat tablets with the different indentations representing, and different areas, there'll be different things they're representing. It could well be that the circular tokens in different boxes represented different kinds of things. There's presumably some code, but it got sophisticated, and we have abstract markings on a piece of clay that represents your net worth. And if that doesn't look familiar, it ought to. 5,000 BCE, we've got credit cards made out of clay. Okay. Okay. That, according to the anthropologists, and this has been this is pretty well accepted in the business, their business, not my business. I'm happy with this. It seems like a good explanation. Is where we have money. Certainly, numbers came out of that area, and this seems the most plausible explanation given the available evidence. Okay. So that's where we get counting numbers. It was for money. But there was another system of numbers. What about the numbers that are used for building pyramids, measuring volumes of things, seeing how much land you own when the Nile Delta, this is the Nile Delta, when the Nile Delta floods and you have to remap the thing. There was measurement. That was going on as well. Now, one of the interesting things about this is to modern eyes, those are both systems of numbers. Those give you the natural numbers, and that gives you what we call the real numbers. But this is a 19th century, early 19th, early 20th century interpretation. These were not thought of as numbers. They were quantities, lengths, volumes. Interestingly, not areas. Areas seems to be cognitively complicated. But lengths and volumes and quantities. So these were regarded as essentially separate. The Greeks tried to combine them, and when they discovered that you couldn't, the famous discovery that the square root of 2 was irrational, they pushed them apart again, and they took that as meaning that you can't marry these with those because of what they call the incommensurables. You simply couldn't use whole numbers to capture this. Only at the end of the 19th century, 2,000 years later, were mathematicians finally able to marry these things together in a single number system called the real numbers. Because that's very, very recent. And this is part of why mathematics got interested in concepts and relationships, because these guys took a lot of building. But the reason they took a lot of building was because these were regarded as foundational. And yet these, from a cognitive point of view, these are both basic. Human beings have a cognition about quantities, discrete quantities. We can count things. We also have a sense of lengths and volumes. We have a sense of continuous size. So the human cognitive system captures both. And it just took mathematics a long time to marry those in a single system. If you read Newton's Principia, where he talks about the calculus, he's not talking about numbers. He's talking about quantities. Calculus, in Newton's terms, calculus wasn't applied to numbers. It was applied to lengths and distances. We interpret it today in terms of numbers, but that's because we have a different conception of numbers. And at that point, I'm going to make one more detour, then we'll take a break. Okay. And this is an interesting one, because it plays in a lot of what we read about education. Now, you know, and this also goes for most of Europe, Western Europe at least. Certainly sort of countries that are essentially capitalist. We build our number system on commerce and trade. Okay, we start with counting numbers and elementary arithmetic. And this is typically how we teach kids in arithmetic. And then we proceed to fractions. Then we introduce negative numbers as best you can. It's tricky, that one. Smart kids ask questions that are very difficult to answer. And then we slip in real numbers under the heading algebra. We pretend there's not a problem there. And from the point of view of a teacher, the first step is pretty good. There are good metaphors for counting. You know, I mean, you can count, and you can think of all sorts of metaphors for dealing with positive numbers. Fractions is pretty good. You can talk about breaking things away. I mean, you know, American mathematics books are talking about pizzas, but I guess that reflects just American diet. European textbooks, we cut up straight lines and squares and rectangles and pies. Actually, we don't cut up pizzas in Europe. We cut up pies, which is misleading because pi tends to mean something else. But anyway. But there are good metaphors about sharing out in fractions. Negative numbers are sort of, you know, you read all sorts of weird stuff about helium balloons on balances and things, which is a really weak and misleading metaphor. But anyway, there's all sorts of problems here, and kids sort of get lost. And many an adult has enormous trouble really knowing what negative numbers are. You know, minus times minus equals plus, the reason why we won't discuss. Was Hilaire Belloc, I think it was. And in fact, most people actually can't give a good explanation of why minus 1 times minus 1 is plus 1. And it's not because they're stupid, it's because it's actually kind of a tricky thing to do. And this is the famous don't ask, don't tell policy. You just don't raise the issue. You just say, well, there's no problem here, we just have these continuous lines. And then students get to university and they look at the construction of the real numbers from the rational numbers and they think, oh, I'm not going to be a mathematician. Okay. And that's more or less the historical thread, starting in Sumeria and going through sort of commerce-driven society. In fact, the rest of today's lecture is going to be about how it came that Western Europe and then the United States was the dominant economic power for many centuries. You know, why is the word banking from an Italian word? Why is the word policy from an Italian word? Why is double-entry bookkeeping coming out of Italy? Why are financial districts often called Lombard Street? Why is all of the terminology about banking and finance and insurance and international trade, why is so much of that Italian? We'll come to that in the second half of the lecture. That was a case where mathematics really drove modern society and gave dominance to first Italy and then Germany, then Western Europe and then the United States, and just took over from the rest of the world in economics. And with it science as well. You know, why is it that Galileo was in Pisa? Why did it all happen in Italy? Something happened there. Well, several things happened, but One of them was to do with this sequence of learning. But there's another way you could learn about them, another educational system, and this one was developed in the Soviet Union. I'm not sure if it's still used very much in Russia. This is known as the Davidoff Curriculum, who was a Russian psychologist and educator, died not that long ago, Vasily Davidoff. And he said we should start with you see, the problem with that last picture was going from the rationals. Well, the negative numbers is a problem, but going to the real numbers is a real problem. You've got the don't ask, don't tell policy. It's really very difficult conceptually. And he said, we've got a concept of measurement that predates by hundreds of thousands of years counting, namely measurements of lengths and things. Most creatures have a sense of distance and length. They use it to sort of catch prey, to swing from tree to tree. I mean, there's an innate sense of distance in many creatures, much more sophisticated than a sense of counting. Discrete counting is much more restrictive in the animal world. Okay, so most creatures, including humans, have this very rich sense of quantitative measurement. He said we should build our number system. We should begin with the real numbers and with algebra, and then arithmetic will drop out as a special case, which is true. Because when you have the real numbers, the natural numbers are just points on a line. And it's just a particular instance of this thing. So he said it's better to begin with this rich sense of distance and volume that we've had for millennia. And in building a curriculum, he took Vygotsky's ideas and talked about spontaneous concepts via scientific concepts. And these are all technical terms, which I won't go into details about, but we can chat about them offline sometime. Spontaneous concepts when children just abstract from everyday experiences. But human beings don't just abstract, they theorize. And they can theorize from a very early age. In fact, they do. I mean, very young children theorize about things. They form theories from a very early age. And he says with a bit of nudging, you can take those ideas, this theorizing capacity, and develop what he calls scientific concepts. And this allows you to build a curriculum in which you get very naturally, at a very early age, from ages something like 6 to 8, you can begin by doing algebra and solving equations, and then arithmetic follows as special cases. If you are interested, I have an online column called Devlin's Angle at the MAA. If you just type in Devlin's Angle, and you go back to 2008 and 2009, Christmas around 2008, 2000, I actually had 2 articles on these. It's actually hard to find out much about this. This is written about a lot in the educational research literature. My 2 articles are almost the only articles I've seen and come across that tries to explain these things to a general audience. But there's another way. And so these different cognitions can be taken advantage of from educational purposes. Okay, how many people use mathematics in their profession? Is that of interest? Oh, quite a few. Oh, quite a lot. Okay. Yeah, I sent out that email, so if you've got anything you want me to sort of touch on, we'll try and so 3 or 4 people have already emailed about topics we can talk about. And then, since there's no strict syllabus, we can just let this go in different directions. It's in a sense, in many ways, it's an open-ended course. I've got enough material on this laptop, to lectures non-stop for the whole year if we need be. That's not the plan. But let me just finish this theme today. And this is really a different talk. And the background, actually, we can't see the background on this one because of the lighting. But I like my keynote, and I tried to choose backgrounds that reflect the discipline. So we had that sort of bright and breezy tour of mathematics with a piece of Wolfram wallpaper behind it. And now we've got something to do with staid financial institutions. And I got a book that looks like a ledger. So you just have to take my word for it that the background here is actually a ledger of a financial book. Because what we're going to be talking about is that point I talked about right at the end, about how it was that Italy and then Western Europe just took a jump on the rest of the world in terms of financial institutions, and how Italy drove the commercial financial revolution in the 13th century. With double entry bookkeeping coming out of Florence with the Medicis the 13th century and a whole bunch of other things happening. And this is in many ways a personal story because a lot of what I'm going to tell you about is stuff that I didn't discover it originally, but I was the one that was able to put together the story by traveling to Italy many years in succession and talking to the Italian archivists and historians and trying to put together a story that was partially known, but in some ways was not completely known. Okay. So here's a picture, actually 3 images I took of Pisa, modern day Pisa, this sleepy place with lots of mosquitoes on the Arno River. But in the 13th century, this would have looked very different because this was one of the world centers of trade. You had Pisa and Genoa and Venice, and to some extent Florence. I mean, Florence and Pisa were ports because of river traffic. And you actually had flat boats going along to Livorno or Porto Pisano in the case of Pisa, and then ships sailing through the Mediterranean. The main international trade was Mediterranean trade, in particular between Europe and North Africa, because in North Africa you had all the Arab-speaking traders who were plying the Silk Route up and down from the Orient. So you had spices and things going up and down, clothing, skins and so forth, beeswax moving around. You have this trade route between the Orient, the Arabic-speaking, Persian-speaking world, and then Northern Europe. And you had places like Bougia in North Africa, I guess Tunisia now, but on the north coast of Africa as one of the main trading ports in the North Africa. And then you have places like Pisa in Italy, and it was their boats sailing across the Mediterranean that was that was international trade essentially. And so Pisa was an extremely busy port. I mean, it was a port even back in Roman times, but by the 13th century, it was a dominant port, and certainly much more important than Florence, which was further up the river. Okay, here's a more recent picture of Italy. And this was taken from a newspaper in 1944, right at the end of the Second World War. And there was a huge battle between the Allies, the Americans and the Brits on one side, and the Germans and the Italians on the other side. And pretty well everything, this was the central bridge in Pisa, and pretty well everything was destroyed. Certainly the bridge and most of the buildings. The main building on what's now the Piazza 20th of September, the main building was sort of okay, but what was almost totally unscarred was a marble statue. All of that rubble around, all of that destruction, and there's this marble statue about 7 foot tall on a plinth that survived. And you can see that statue today. This is a picture of the square today. It's been restored and everything's been rebuilt. This was actually, I took this about 10 years ago when I began the research I'm going to tell you about. I actually have a picture of me standing there, but vanity prevents me from showing you that picture. But I couldn't resist standing there. And I'll tell you, the reason I got interested in this is because this statue is of someone who, in many ways, whose career was very similar to the one I was having, for reasons I'll mention. So I saw him as a 13th century hero, if you like, a forefather of the way I've run my own mathematical career. And that's his statue today. It's now been fully restored, except for a few fingers missing on the hand, which may have been damaged in the war, in the fight, or they may have been just chopped off by Allied soldiers who wanted a souvenir. It's not clear. But it's in the Camposanto, which is just behind the Leaning Tower in that square, the Piazza de Miracoli in Pisa. And it's a statue of the person generally known as Leonardo Fibonacci. And I'll spend the next few minutes telling you about Fibonacci, because most of what you think you know about him is wrong. And this whole thing is this is a myth-shattering talk. But I want to try and change your views about Fibonacci, because all of us in the modern commercial world who live with the products of modern commercial activity are living the legacy of Leonardo Fibonacci. So let me tell you a little bit about him. He lived we've no ideas of exact dates, something around 1170 to around 1250. Spent most of his life in Pisa. His father was an international businessman. We do know that. And he was a representative of the city of Pisa. So Leonardo grew up in this trade capital of the world in a family that was a leading international trading family. That was his background. Then, when he was a teenager, his father went over to Buja in North Africa to represent peace and trade there, to sort of do customs work and be a trade representative, and just generally be the peace and representative in North Africa. And his son was very gifted in arithmetic. There wasn't any mathematics. This was 13th century. Mathematics was just learning a little bit of rote arithmetic, a little bit of geometry maybe, not necessarily, not clear he did. But he was gifted in it, that was for sure. And so his father invites him over because he wants to bring him into the family business. He wants him to learn trading, to use his mathematical abilities, arithmetical abilities to help his father in the trading, and to learn Arabic, because you had to be bilingual in Italian and Arabic in order to be a successful trader. So it was a natural thing to bring his son over. It wasn't necessarily natural to bring him over at a young age, but Leonardo was, we know, a gifted kid. So when he gets there, he observes the Muslim traders using something that just really wasn't known in Europe. It was known a little bit in what was then Muslim North Spain, but very little in the rest of the world, rest of Europe. It was a system of arithmetic we use today, what we call Hindu-Arabic arithmetic. You know, the 10 numerals, 0 through 9, addition, multiplication, subtraction, division, all done by lining up the units columns, lining up the tens columns, lining up the hundreds column, performing algorithms. Essentially the algorithms we teach today in the schools. Okay. Now that system had been invented by Indian mathematicians in the first 6 or 7 centuries of the first millennium. Then these Arabic-speaking traders who were trading down to the Orient and trading in India, they learnt it and they started using it in their trade. And next week we'll look at how they took it in a direction that we can now call algebra. Algebra being an Arabic word, al-jabra. So that came from the Arabic-speaking traders in essentially Baghdad area. But this arithmetic method was invented in India, developed in India, carried up the Silk Route as a method of doing trading efficiently. And then Leonardo joins his father and sees them using this in their trading. And is clearly very impressed by how efficient it is. Because what the Europeans were doing, and that includes the Medicis and everyone in Florence and all of the accounting people that were setting up shops and the bankers that were all beginning in Italy at the time, what they did was they wrote all of the numbers down in Roman numerals. Okay, it was Italy after all, and that was their invention. So it was all written in Roman numerals, which makes addition and subtraction trivially easy, and multiplication and division impossibly difficult. So it wasn't a very efficient method of calculating, and it had all sorts of other problems. And what they did for calculation was they had 2 methods of calculating. One was what we now call an abacus, or we should call it an abacus board, because we think of an abacus as beads on strings. Well, that was a Chinese invention, the huanpan. That's something different. What the Europeans used was a board with ruled lines and pebbles that you moved around. And so they did the arithmetic by moving pebbles on a board, on what we call an abacus board or a counting board. That was one way. The other way was they used the fingers. They had an elaborate system of doing arithmetic on the fingers of both hands that was good for numbers up to 10,000. It was a pretty complicated coding system. You had to learn it and be very fluent at it. But I'm prepared to bet that if one of those guys could be transported here today that was good at it, they could beat me with an iPhone calculator, because they didn't even have to type it in. It was all on the fingers. So, so it would be even faster than these whizzes on a mechanical abacus, because they were just moving the fingers. So, but they had this very elaborate system. But that meant you basically had to hire someone who could do that. So your pocket calculator was a small person who was very good at doing things with their fingers. I mean, you probably wouldn't put them in your pocket, but that was it. Okay, so here's the story summarized. Developed in India in the first 7 centuries, learned, used and carried northward by the Arabic-speaking traders, and hence we call it Hindu-Arabic arithmetic. Okay, so it reaches North Africa, Leonardo sees it and is mightily impressed. So much so that when he goes back to Pisa a few years later, he travels around the Arabic-speaking world and sort of learns Arabic as far as we know. And when he goes back, he writes this mammoth book called the Book of Calculation. It's in Latin, and he does what every writer's agent tells you to do. If you want to write a business book that sells, you invent a new word. or you change the spelling on an old word. So he changed the spelling and puts an extra B, because this wasn't the book about the abacus, this was the book about doing away with the abacus. And so he's smart. By the way, one thing I think you're going to realise is Leonardo was the Steve Jobs of his era. And I mean that absolutely, in all details. He knew about style, elegance, aesthetic, and marketing, big time. And he could take somebody else's idea, mark it, package it, and put it out so that the world can't imagine ever not wanting it. And that was his greatness. He was a great mathematician, but he had something other mathematicians don't have, which is a salesman's touch. Okay. He completes that book in 1202. That book is generally credited with bringing the Hindu-Arabic number system and its arithmetic to Europe and launching the modern Western world. Okay. Now this is so-called, this is folklore. Every one of us that goes into mathematics, we pick this up at about the same time we pick up that Bernoullis equation is what keeps aircraft in the sky. Okay. But it's like all these things, there's some truth in it, but the story is a little bit more interesting. Okay. First of all, who was this guy? Well, his name wasn't Fibonacci. They didn't have surnames in those days. It was just Leonardo. Okay. If you look at this book, Liber Abaci, and this is the beginning. I've actually held this book in my hand. It's a 13th century manuscript. And this is an image taken from the top of the first main page. It's in Latin, and when you translate it, it says, "Here begins the book of calculation, composed by Leonardo Pisano, Leonardo of Pisa, family Bernacci in the year 1202. Okay, family Bernacci. That actually is a translation of the Latin term, well, Filius Bernacci, which literally means son of Bernacci, but that's not what it really means. The name Fibonacci actually was given to him by a historian in the 19th century who gave him a modern surname, because it's good to have a surname to talk about people. You know. Leonardo himself would have just been known as Leonardo Pisano, Leonardo of Pisa. That phrase, family Bernacci, literally son of Bernacci, in Latin is Filius Bernacci. So Fibonacci is just the origins of the phrase Fibonacci. It's just a derivation from Filius Bernacci, given to him in the 19th century. He does, however, distinguish himself by calling himself son of Bernacci in there. That wasn't that common, but he did it. He almost certainly did it. There are several reasons to be fairly confident that when Leonardo wrote that book, at least when he wrote the version of that book we have, he knew this was a big book. And the version you're looking at was actually not the 1202 version. He wrote another version 20 years later, actually 26 years later, by which time he was famous and the book was famous. So the words we actually read were written when he knew that this was a big deal. And he was interested clearly in cataloguing that. But he was really just saying, I'm from the Bernacci family. Okay. But that at least is the origin of the word Fibonacci. So his name is new. As soon as you hear the name, you think of this thing called the Fibonacci sequence, which is why we're going to be talking about these things next time, because we're going to recognize that almost everything you thought you knew about the Fibonacci sequence is complete nonsense. And don't even begin to talk about the golden ratio. Actually, we will talk about the golden ratio. Pick any fact at random about the golden ratio and it's probably false. Probably false at random, okay. It's a small space, but most of them are false. Okay, it was given that name, that sequence of numbers was given that name again in the 19th century after the name Fibonacci was given. It's an irresistible name. It sounds like, an Italian restaurant or something. Or one of the bad guys in Prison Break, if I remember correctly, was called Fibonacci. But it's actually an invention. It sounds like people have been called that forever, but it was a 19th century invention by the French of all people. Right, so there we go. What's the connection between the Fibonacci sequence and Leonardo? One tenuous connection. Liber Abaci is a mammoth book, 600 pages in the English translation. There only is one foreign language translation. It's an English language translation that was completed in 2002. as it happens, 1,000 years after the original, 800 years after the original one. Well, first of all, what he does in this book is he describes modern arithmetic. Now, Leonardo is describing modern arithmetic to an audience who've never seen modern arithmetic. They haven't seen the numerals. The book begins by explaining, here's how you write a 1, here's how you write a 2, and then really recognizable, here's how you write a 3. So he tells you how to write them, then he tells you about the units column. He tells you all of the stuff we teach in elementary school and kindergarten now. But he's doing it sort of remotely. It's like me giving my online course. He's not seeing a lot of stuff, he's writing a book. So he spells it all out in great detail, and then he gives hundreds of examples. Mostly they're about trade and commerce, because this book is meant to revolutionize trade and commerce. So there are pages of examples on currency exchanges, on weights and measures, on alloys. You had to be good at alloys because all of the coinage was different in different cities, and they had heavy metals and so on. But you had to be able to talk about the alloying of metals in order to know how much the currencies were worth. You had to convert currencies, you had to convert weights and measures, you had to weigh things, you had to work out profits and losses. All of the stuff of business had to be explained. So there are hundreds of these examples from business. In fact, he does it very much like a modern calculus textbook. He makes sure that if you have a real problem, you can eventually find one of his examples that's almost identical and you just change some of the numbers. So it really is a cookbook for doing arithmetic, which means it's unbelievably boring. Right? I mean, this book is thick, and I can't claim to have read it, but I've probably read more of it than anybody else because I was doing this research, and it was heavy-duty stuff. But he's not stupid. He realizes that every now and then he's got to throw in a bit of light-hearted relief. So every few examples, he throws in a whimsical problem, a little puzzle problem. Things like, a lion drops into a pit. The lion can climb up two lion lengths and then slide back 1 lion length. How many days before it gets out the top? All these sort of classic puzzles that you get in Christmas crackers and things like that if you go to Europe. And he throws these in, and one of them is this whimsical problem about a rabbit population. And it's a good problem because in order to solve it, it's a good use of the algorithm for adding numbers together. Okay. And you get this famous sequence, the Fibonacci sequence, which is up there, which we'll talk about a little bit next time when we look at pine cones and things like that. And then you get to the answer. So it's a whimsical problem that still has an educational purpose. Well, a couple of things need to be said. This wasn't his problem. It was known well before then. It goes back hundreds of years. All sorts of writings refer to this problem. There's no reference to this problem anywhere else in anything he wrote. He's a smart guy. He wasn't going to spend his time working out fictitious rabbit problems. It was just a fun problem he threw away. That's the only connection between him and this sequence. So claims that you will read that he was interested in it, that he invented it, that he discovered it, no evidence for that whatsoever. He just threw it in, and it was a standard example that he probably learned as a child, and he just throws in to lighten the load. So it's kind of sad that this is his popular legacy. Fibonacci is the Fibonacci sequence, because the guy has a legacy. Here it is. This is the quote from William Gertzman, who's a professor of finance and management studies, director for the International Centre for Finance at Yale University. The 500-year period following the appearance of Liber Abaci saw the development in Europe of virtually all the tools of financial capitalism that we know today. Share ownership of limited liability corporations, long-term government and corporate loans, liquid and active international financial markets, life insurance, life annuities, mutual funds, derivative securities, and deposit banking. Many of these developments have their roots in contracts that were based on the mathematical analyses Leonardo introduced to Western Europe. That's one amazing legacy. It's a little bit more important than a fictitious rabbit population. And he actually goes on and says, the things that... I'm not sure we're supposed to talk about these things now since the financial crash. But anyway, according to Gertzman, you can look at Liber Abaci and you can trace back the beginnings of present value analysis, which has certainly been claimed to be used by all large companies in making big capital budgeting decisions. This is actually in a very large book, Origins of Value. So this is the modern financial world traced back pretty clearly to Liber Abaci. Okay, so he's got one amazing legacy. Now, no one's claiming that Leonardo invented anything in there. What he did was gather this material, systemize it, and write it in a very accessible way. It was like Euclid did with elements. It's not clear that Euclid did any of the mathematics that was in there. He might have done. But he made an incredible job of collecting it and presenting it. And Leonardo certainly made an amazing job of presenting this material in this mammoth book that captured hundreds of years of development, beginning with the Indians and then all of the Arabic-speaking, Persian-speaking traders that developed it and grew it. And he presents it in a way that can be used. Okay, now here's that first page. Here's the whole of that first page. And this is a copy of the book. He wrote it in 1202, but then he wrote a second version in 1228. And this is a copy. It's not in his original hand. Nothing in his original hand survives that we know of. But this is one that was written before the end of the 13th century, we think. Might have been early 14th century. But it was a very early copy. It's one of only 3 complete copies that exist. And I've actually held 2 of them in my hand, which is kind of awesome. The first edition hasn't survived either in his hand or anybody else's hand. There might not have been many copies of the first edition because he brought it out and he wasn't famous. But 26 years later, he was really famous throughout Italy. Okay. And then the Emperor Frederick asked him to write a second version, and he wrote it and dedicated it to the Emperor Frederick. Because by then, he was a big shot in Italy, and Italians knew the importance of this stuff. You know, they were taking this and using it to build new businesses. So he writes a second version in 1228, and there's about 14 copies in existence, and 3 of them are complete copies. One in Siena, one in Florence, and one in the Vatican Library. We also know from things he wrote that he wrote a second version, a smaller, simpler version, called Book in a Smaller Manner, aimed at the merchants. Because he's got this big book, which lays it all out in, but that's really a reference book. He knows that practical business people want the short version that you can buy in the airport. Well, I guess there wasn't an airport, but you know the kind of things, you know, finance for dummies. You read it on the plane and then you go and make a deal. I actually met people who made a lot of money doing that. I met one guy who read this book called, what was it called? Something like Financial Derivatives for Dummies or something, and actually went and made a lot of money in the business. At least that was his creation myth. Okay. Because it was known to be written, most historians assume that this was the book that really made the difference. The first book, Liber Abaci, the big one, sort of established the credibility. It says this is all for real. And then he wrote an easy learning book, a sort of a pocketbook edition, that was widely believed to be the book that people actually learnt it from. Because it was clear that the Italians were learning this stuff very quickly in the early 13th century, because they were developing all these modern financial institutions. He wrote some other books. The trouble is no copies of that thing were found. Okay. So we don't even know what was in it. He writes another book. In between that first and second edition of Liber Abaci, he writes another book on geometry, practical book on sort of geometry for carpenters and for people that are cutting up cloth and things. So it's practical geometry for, all of this was very practical stuff. Because he's famous, he goes on the 13th century equivalent of jeopardy, which means you get called to the court of the emperor when the emperor had his court in Pisa, and Leonardo went in front of an audience like this one, and the audience gave, or at least actually representatives of the audience, actually representatives of the court, gave him challenging mathematical problems, and he would demonstrate his virtuosity by solving the problems in front of the audience. Like all good game shows, he was clearly given the problem in advance. Right? But the fact is he actually got some incredible solutions, and he gives the solutions in a book that he wrote for some of the best 4 solutions. He writes in a book he presents to the emperor called Floss, the flower. So he's a famous guy then, and this is a demonstration of his ability. He was undoubtedly the best mathematician for many, many decades, if not centuries at that time of history. And then he writes one of the first books on modern number theory, the Book of Squares, the kind of stuff that leads up to Fermat's last theorem, looking at Pythagorean triple. So he writes a sort of a recognizably modern arithmetic book. All of these now exist in English translations. You can get them. Well, that was the story, at least that was the state of affairs until 2003, when a historian, or at least an archivist, discovered a manuscript in Florence that is almost certainly, really almost certainly, one of the earliest copies of that lost book. So we've known for just under 10 years what the contents were of the book that gave the modern financial world that we know, which is pretty darned awesome. Let me tell you the story. Okay. This is the sequence of events. This was the world's first computing revolution, personal computing revolution. You know, Silicon Valley was the second one. And we'll take Steve Jobs as the iconic figure of the second personal computing revolution with the Apple II. Okay, that's as good as any. And we'll take Leonardo with Liber Abaci as the first one. Okay, so this book comes out in 1202. In the 1960s, historians in Italy started uncovering not tens, but hundreds of handwritten manuscripts, not in Latin, but in vernacular Italian, that were how-to books on practical arithmetic. Hundreds of them. And those are the ones that have survived. There was a cottage industry of people copying these books all over Italy, beginning soon after Liber Abaci comes out. Hundreds of these things. And the archivists just kept coming across these things. Huge numbers of them. Of the ones that have survived, you know, this is a revolution in the 30s. This was pre-Twitter, right? So it took a while for the word to get around. These were handwritten manuscripts. So you have to talk in terms of a year maybe to copy a manuscript, maybe 6 months for a shorter manuscript. So it was a slow process. It was a one at a time manuscript copying. So of these manuscripts, 250 have survived in really good condition. One of them dates before 1300. We'll come back to that one. 8 of them in the next 25-year period. Then 10. Then there was a lean year. These are the ones that have survived. So then 6, then 19 that survived, then 16. So there was a steady growth of these things. And then eventually they died out. They more or less died out in 1501 or by 1501 for reasons that you can probably guess, but we'll come to anyway. But we can infer, since these are the ones that survived, and these were not valuable books, they were just handwritten copies by unknown people. If 250 have survived in good shape, there were probably thousands of these things. There was clearly a huge demand to learn modern arithmetic. And it was manifested in all of these financial institutions that came out of Pisa, then Florence, then up to Venice, then into Germany, and then around. You know, there was a period in the late 13th century where the Germans would flock to Venice in their dozens to learn how to do this stuff. In fact, they built a complete hotel in Venice for German business people to come and stay while they learnt this stuff. At the same time these books came out, there were what's known as abacus schools. All over Italy there was these night schools like Stanford Continuing Studies where you went to learn how to do arithmetic for yourself. Okay, and you probably paid for it as well. In fact, it's believed that Leonardo opened one of these schools. It's surmised that he opened one of these schools. It's not, we can't say believed. He probably did, but there's no evidence either way. The earliest known one was in Verona in 1294, but they were probably all over the place. And Florence alone had maybe 20 of these things. They certainly had 20 by records that exist. So there were these schools, this huge demand that was being met by these books. And then you've got all of this activity, all of these books on practical arithmetic, most of which, by the way, began with a passage that says, this describes modern arithmetic in the style of Master Leonardo of Pisa. They almost all of them, or many of them, let's say, acknowledge that this was Leonardo's teachings that were being passed on. So there was clearly an acknowledgement that this was coming from Leonardo's work. And then suddenly he disappears from the history books. There's no more mention of him. Huge influence on Italy and on commerce and trade. And then he was suddenly forgotten, and the reason was modern technology. The printing press comes along, and no one's going to waste their time copying a book by hand anymore. The first book we're told that was printed was the Gutenberg Bible. The second, or maybe the third, was a book on practical arithmetic that was printed in Treviso a few years after the Bible. So one of the first ever books that was printed was a book on practical arithmetic. Now, if you're a printer in Treviso and you're trying to rush out a copy in print of this book that you know is going to sell by the thousands because there's a huge demand, you're not going to go to an Italian, to a Latin book and translate it and mess around. You're going to pick a recent book. You're going to pick something that's been written fairly recently. First of all, because when these people wrote these modern books, they updated the currency, they made them localized, they made them relevant to their local community. And in Tuscany at that time, there were dozens of different currencies. So there were all these different currencies, different ways of weighing and measuring. So if you wanted to sell a book or make it available in your neighborhood, your district, you had to personalize it. You brought it up to date with the coins, with the local weights and measures, with the problems. The examples had to be realistic. So you modernized it. So the printer in Treviso, who printed the first arithmetic book, now known as the Treviso Arithmetic, would have picked a fairly recently written book that was local to Treviso. And then that just gets printed and distributed. So suddenly you've got a standardization coming in built upon one of the later of these abacus books, by which time Leonardo had long been forgotten. And there was only one exception. There's a very famous mathematician called Luca Pacioli, who was a contemporary and a friend and a colleague of Leonardo da Vinci. And in 1494, he wrote this book about arithmetic, geometry, proportions and proportionalities. And there's a relatively modern version of that. And in the beginning of this, he has this phrase that says, and since we follow for the most part Leonardo Pisano, I intend to clarify now that any enunciation mentioned without the name of the author is to be attributed to Leonardo. Now, Pacioli is a famous guy. He produces a printed book and is a friend of Leonardo da Vinci. So he's a big shot. He gets noticed, his book is going to be preserved, and in his book, he acknowledges where it all came from. That's the only historical record that links the world of the printing press and printed books with Leonardo in the 13th century. This book with that annotation is known, it lies around until a historian comes along, looks at this book and said, who is this Leonardo Pisano? I've never heard of him, and starts to dig around to find out more about him. And with this one little thread, historians began to put together the story, part of which I've told you, and the rest of which I'm going to complete and finish you. Okay. So the story begins to be put together that Liber Abaci gets written, big demand, abacus books, abacus schools, people learn about it, develop modern financial commercial transaction systems, and build the modern financial world. So the supposition was, you've got Liber Abaci, then you've got the books that people actually learnt from. Because they certainly weren't reading Liber Abaci. First of all, they couldn't read Latin. It was dense. It was like Euclid's Elements. It was full of proofs and theories. They wanted a much more practical book. The examples were practical, but it was written very theoretically. This was solid mathematics written with practical examples. These books were all simplified and written in much simpler language, and they were in vernacular Italian. So the question was, how did the material get from that big manuscript, of which there were very few copies, to the many hundreds of these manuscripts? The problem was, by the way, it was hard to see how the material got from one to the other. Here's one. There were a lot of problems. The biggest problem was this one. We've got several copies of this, and all the copies differ because they're hand copies, but they're all more or less the same. They're just minor differences. You compare any two of these, and it was clear that they were copying from each other. Whole passages were taken from each other. So they were clearly, everyone was copying from everybody else. Many passages, you pick any two of these and you probably find some common passages. So it was clear these were all copying from each other. The problem was, none of these contained a passage that could be found in here. It wasn't that they'd taken some of this and started it. These were all clearly going, if you trace these back, they went back to one or two manuscripts which weren't that one. So whilst everybody acknowledged that the material that was in here, the mathematics found its way into here, the way it was expressed didn't. So there was this big question. And there were other issues, but the biggest issue was these all had things in common. They had nothing in common with that. Okay, the supposition was that Leonardo's little book for merchants was the link. Because someone had to have taken the dense mathematics in Liber Abaci and produced a simple version. There's only one person that was known to be alive at that time that was probably capable of doing that, and that was Leonardo himself. So the supposition was always Leonardo's book for merchants was the beginning of the true revolution. But we didn't have a copy. We didn't know what was in it. So that was supposition until 2003. And what happened in 2003? Well, it's just before then, because 2003 was when this person published the result. There's a lady who I became a good friend with, Professor Raffaella Franchi at the University of Siena, at the Center for Medieval Mathematics. She's a mathematician who turned into a historian. And back in 2002 or thereabouts, she steps through this doorway. This is about 100 meters north of the Duomo in Florence. And you go through this door, this little nondescript door, in the Via del Gennari 10. And I actually went through this door. I actually went through this 2 years ago for the first time and retraced her steps. And it was kind of awesome. This was in the middle of summer. I was up in Florence, and hot day outside in the tourist, and you walk through that doorway, and you're hundreds of years in history, just through a doorway. You're in this great historical archive. You're in this room, the Riccardiana Library, which is now a public library. It's part of the National Archives of Italy, but it was for many years a private library. It's purely a reference library full of, must be billions of dollars, untold value of ancient manuscripts. If I've got time at the end, I'll tell you how I managed to get in there. It wasn't. This is one of the few places, it's one of the few libraries where a Stanford identity card won't get you in. But, that Stanford card, I've got used to the fact that that opens many doors. It doesn't get you through that door. I got through that door because I have a North of England accent, and we can talk about that in a minute. Scholarships sometimes depend upon things like what sound you make when you open your voice, open your mouth. Here's what I went to see. This is a book. It's the one abacus manuscript that we know that dates before the 1300. It's called Codex 2404. It's been in that library for hundreds of years. As far as I know, Franchi might be the first person to look at it. I may be the second person to look at it. I kind of worry that having started talking about this, it's going to become a tourist attraction. But you need more than a Stanford library card to get you in there. From the way it was written, we know it was written by an Umbrian. We know it was written by someone who really didn't understand mathematics. It was just copied from something else. It was clearly a copy. And you can make all sorts of other inferences. But because of the way the coinage worked and everything, the date can be put pretty precisely. Because the currency's changed, and one of the ways you can pinpoint when these books were written, most of them didn't have a date on them, but you can pinpoint them. This is great. This is literary forensics. You can pinpoint them by looking at the values of the currencies and looking at the mathematical problems. From the kind of mathematical problems, how they were couched, you could, and you can also infer which they were copied from in later editions. You could find which was copied from what by how the currencies were changed. By the way, the Fibonacci rabbit problem is in here, but it's about pigeons. For some reason, this guy preferred pigeons, and he changed it to pigeons. That probably tries to get it out of copyright or something. Actually, there wasn't any copyright then. He begins with this. Now, we have to be a little bit careful about that statement. Everybody put that in. But that's just name dropping. By then, Leonardo was famous. So if you're a nobody writing a book, it was actually good to write that. Even if you had no idea who Leonardo was, you knew. It's like going to a party and saying, well, I was talking to Steve Jobs the other day. I never did talk to Steve Jobs. I stood behind him once in a coffee shop, but that's as close as I got. Okay, but it's like name dropping. So everyone did this. It sort of added respectability. So you can't really assume that he necessarily read that. But when you look at this and you combine it with all of the other evidence that was available, it's pretty clear that what this is a very, very early copy, possibly a first copy of Leonardo's book for merchants. There's so much evidence that comes together that the literary forensics people have put together. That all of that evidence was available, that once this manuscript was discovered and identified, this was clearly it. And Franchi was the one that wrote the first paper on this thing. So now we've got a copy of the missing link between this mammoth book and the Abacus books that came. This was a book that was sold in New York about 6 months ago for several $1 million, I think. It was a copy of one of those. Okay, let me just finish by giving you a couple of images of those manuscripts I've been talking about. Here's the Siena Public Library. This was just before the Palio, one year when I went there because the flags are there. Interesting thing about this is the public library. That book is a public book. You can walk in, as I did. You don't need a Stanford Library card for this. You can just walk in and say, I'd like to look at Liber Abaci, and they'll bring it to you. They'll take your passport in exchange, but that's all. You know, amazingly easy there with rare manuscripts. This is a 13th century manuscript, one of only 3 that exist. And they let me look at it for a couple of hours with nothing more than my passport in their possession. Okay, so and I got them to make a couple of images of this manuscript. So this is the early Liber Abaci. Worth noting, the numerals were written in red because these were different. The mathematical symbols were written in the margin. We tend to think of mathematics as being symbolic, and you use the words to describe the symbols. That's the way we do it with the printing press. Before the printing press, if you were an author, you knew that the scribes who copied it, very often they were monks, were pretty good at copying text, but they were hopeless at copying symbols. So the chances are all the symbolic representations would get lost or screwed up. So if you were a mathematician writing a book like Leonardo was, the mathematics was described in words, and the symbolic stuff, the stuff that depended upon the array, was an illustration in the margin. And that flipped with the printing press. But pre-printing press, you wrote down everything in words. And you wrote the symbol, the numerals in red. That was fairly standard. There's another picture taken from the book. Here's the one in Florence. There's the Florence National Central Library. And here's the same manuscript, but the Florence version of it, slightly different color, but the same contents. So again, you're looking at a 13th century, maybe early 14th century manuscript. Everything you needed to start a business was in that book. And here's the book from the Ricardiana Library. This is the book for merchants. And if you're interested in more of this story, I ended up writing 2 stories. I wrote a book, a classic book, about the story I've just told you, about how Leonardo wrote his book and so forth. And then there was a really interesting feature of this, and we actually are out of time, so I'll just say in 2 words. As I was doing that research, what struck me, and it took us 10 years to collect all that together, what struck me was how similar was the story of Leonardo with the story of Steve Jobs and the founding of Apple, and in particular the release of the Macintosh. And so I ended up writing not a book, but an e-book that could be sold on the apps, by Apple on their store, about Leonardo and Steve. And in that book I take Stephen Levy's book, Insanely Great, and I basically went through it and replaced Jobs by Leonardo, Lisa by Liber Abaci, and Book for Merchants by Macintosh. It was the same story. Leonardo sees the idea, recognizes how important it is, writes a big book, the equivalent of the Lisa at Apple, realizes that $20,000, the Lisa is not going to be a big seller. You make a smaller, simpler, neater version, and Leonardo does the same. He makes a simpler version that takes off like hotcakes. And so I literally just took Stephen Levy's book and then side by side told the 2 stories. And it's incredible how many details that was similar. All right, that's the end of today's story. Look forward to seeing you next week.
For more, please visit us at stanford.edu.